Hey there, in this video we're going to talk about the definitions of limits. So what is a limit? We'll start with having a discussion for this graph. So we're going to graph the piecewise function defined by the square root of x for x's, all the values of x that are less than 1, and the square root of x when the values of x are greater than or equal to 1, which makes sense because of the domain of the square root of x. We want to make sure we don't have any negative numbers. So what does the graph of that piecewise function look like? Well, what does the square root of x look like individually? So here we have y equals just the square root of x. And so we have the v shape. What about the square root of x? What does that look like? And I have the square root of x over here. And so we notice that the split point, right, I call this over here, x equals 1 is our split point. So I'm going to go to 1. So when x is 1, and we're going to see what is that value. And so that's the absolute value of 1, which is 1. So this is the point 1, 1. Now notice that it says when x is less than 1. So we are not going to include the value right there when x is equal to 1. So that's going to be an open circle. And when x is less than 1, we look like the absolute value of x. So that means we're going to take the part of the graph that is on this side when x is less than 1. So we're going to look like the absolute value of x just from negative infinity to 1, not including 1. And then when x is equal to 1 and greater, we're going to look like the square root of x. So same thing, we're going to identify our split point, which is x equals 1, and then we're going to go to the graph and notice that that is also 1. So this is also the point 1, 1. But here, because x is allowed to be 1, right? X is equal to 1. The square root of 1 is 1. So we're going to fill this out. And for this graph, we want everything that is greater than 1. So essentially this domain, greater than or equal to 1. So the domain is always, one good way to think about the domain is that is the shadow of the graph. So when x is less than 1, the shadow that we want is from negative infinity to 1. So we only want that part of the graph that makes the shadow when x is less than 1. And then for the shadow of the graph, when x is greater than or equal to 1, we want it to be the square root of x. Now putting it together, infinity to infinity, we take from the left of 1, we're going to take the absolute value, and to the right of 1, we're going to take the square root. So putting it together, what does that look like? So here we are. So notice that when x is, so let me put our split point again, of 1 over here, and this is the point 1, 1. Now it ends up being that this one, because the values coincide at the point 1, 1, this blue graph is going to fill in the open circle that we had from the red graph. So that's why you don't see any holes in this graph. And of course, this keeps going to negative infinity on the x, positive infinity, so we have the entire domain. So this is what our graph looks like. So when I ask what is the limit, so the limit as x goes to 1 is asking you of f of x, is asking you what are the y values doing. So what is the behavior of the function? The behavior of the function values being the y values. So what are the y values doing or approaching as x approaches 1? So when you see a limit like this limit notation, limit as x goes to 1 of f of x, this is asking you a question. What are the y values doing, right? What are the function values doing as the x values approach 1? So as our x values approach 1, what are the y values approaching? You can see that the y values are also approaching 1. So in this case, we will say that the limit as x goes to 1 of f of x is equal to 1, right? So as the x values approach 1, the y values are also approaching 1. So let's talk about what is the formal definition of a limit. So our definition of a limit is that for any function of x near a, except positive at a, if f of x is arbitrarily close to L, some y value, for all x sufficiently close to a, we write that the limit as x goes to a if f of x equals L. And so that is what we say, the limit, as f of x approaches a equals L. I'm trying to read it and say it at the same time in my brain. They're not connecting. Okay, so let's try this example. So graph g of x, and we're going to try to find the limit. Now, what limit do you think we're interested in finding just based on the function? So here, my limit definition is the limit as x goes to a of f of x equals L. So as x approaches a, the y value is L. So here, when we have a piecewise function, we're always kind of interested in knowing what happens at the split point. So the split point here is x equals 0, so I want to know what is happening there. So we want to know the limit as x approaches 0 of g of x. My function name is g in this case. So what is this equal to? So again, remember what the question is. What are the y values approaching as x approaches 1? So in this case, what are the y values approaching as x approaches 0? So when we have a graph, we can just look at the graph. So let's graph this and see what we get. So what does x squared minus 1 look like? And we only want it to look like x squared minus 1 when x's are less than 0. So here's our graph of x squared minus 1. So let's say this is y equals x squared minus 1. Right there is minus 1. And our split point is x equals 0. So x equals 0 is over here. So we're looking at when x is less than 0. So x is less than 0 means to the left of 0. And so I want this part of the graph, the left side of 0. And so we're going to get rid of that one. And then when x is greater than or equal to 0, oh yeah, so that one is not included, so that means we're going to have an open circle there. And when x is greater than or equal to 0, we look like y equals 2x plus 1. This looks like y equals mx plus b, so this is a line. So let's look at what that line looks like. So here is our line. And so this is, I'm going to write it over here, y equals 2x plus 1. And we want to look like this line when x is greater than or equal to 0. So again, 0 is over here. So we're going to go to the function value, so which is there. And because x can equal 0 there, that means that the y value is going to be included. And so we want this side of the graph. When x is greater than 0, so we want the right side. So we're going to put it together, right? Left side of 0, right side of 0, we just look a little different. So I don't want this part. And so let's put it together. And so this is what we look like put together. So our split point is at x equals 0. Now just to make this graph a little more accurate, that is open circle. I'm not included, that y value is not included, and this is a closed circle. Now remember, these are still functions, and so they have to pass the vertical line test. So if both of those were solid, this will not pass the vertical line test, and so it will not be a function. But it is given to me as a function, so I have to ensure that it passes the vertical line test. And so this is the graph of g of x. And so what is happening? What is the limit as x goes to 0? Remember, the limit as x goes to 0 of g of x is asking you what are the y values doing of this function as x approaches 0. So let's see. As x approaches 0, what can you say about the y values? You're probably thinking, well, it depends. How am I approaching 0? Am I going from the left or from the right? And that is a really good point, because notice that to the left of 0, when we're following the parabola, the y values are approaching -1, right? That is the y value equals -1 here. So that's what we're approaching. But as x approaches 0 following the side of the line, our y values are approaching, right? If I pick an x here, that's my y value. X here, that's my y value. So that's what these lines represent. So I'm approaching 1. This is my y equals 1 over here. So what can I say about this limit? In this case, we say that the limit does not exist. So notice that the limit as x goes to 0 of g of x changes, right? The y value changes depending on the function, depending on, the side of 0. So are you to the left of 0 or to the right of 0? Because then if your x value is on the left of 0, then your y value is approaching -1. And if your x value is to the right of 0, then you're approaching 1. So because the y values are changing, we say that this limit does not exist. That's therefore. So the limit as x goes to 0 of g of x, we say does not exist. And this is abbreviated DNE, and essentially it just means that the y values don't coincide. Or we can say it's not approaching a single y value. So let me say that. So it's not approaching a single y value. So in our first example, notice that as x went to 1 from the left, we're approaching 1. As x approached 1 from the right, the y values are still approaching 1. So the limit is 1. Right? The limit is asking what y value are we approaching. In this example, as we approach 0 from the left, is going to -1. The y values are going to -1. And as we approach 0 from the right, the y values are approaching 1. So the limit, right, the y value is not approaching a single y value, so it does not exist. So that's what that means. I'm going to stop it there for this video. In the next video, I'm going to talk about what does this mean? The left side and the right side, because those have special names. So we're going to have a left-sided limit and a right-sided limit. And the limit is going to exist when those coincide, when they're the same. So in my next video, I'll do examples of one-sided limits.